Hello friends, myself Priyanka from Bsc Chemistry Honors Final Year. Today we will discuss the chapter of Physical Chemistry and the topic is electronic spectra. It has been discussed in the last chapter that when molecules absorb energy in the microwave region, that is far infrared region, transitions between the rotational levels take place giving rotational spectra. Similarly, if the energy is absorbed in the near infrared region, transitions take place between the vibrational levels accompanied by those in the rotational levels giving vibrational rotational spectrum. However, if the light is absorbed in the visible region or ultraviolet region, electronic transitions take place giving electronic spectra. A number of other processes also take place on absorption of light called photoprocesses. These may be photophysical processes such as fluorescence and phosphorescence or photochemical reactions. The branch of science dealing with such processes is known as photochemistry. In the present chapter, we shall take up a brief study of electronic spectra, whereas photochemistry will be discussed in the next chapter. Electronic transitions and band spectra. Theory of electron band spectra. Just as there are electronic energy levels in an atom, there are electronic energy levels in a molecule also. However, there are no simple formulae available for the energies of these electronic levels except for the hydrogen-like atoms. Electronic spectra are obtained when the electrons in a molecule are excited from a lower electronic energy level to a higher level. However, as the electronic transition is accompanied by vibrational and rotational transitions, the total energy of the molecule in any state is the sum of electronic energy. If E electronic, vibrational and rotational represent the electronic energy, vibrational energy and rotational energy respectively of the molecule in the initial state before transition, and E-E, E-V and E- are the corresponding values in the final state after transition. Then we have energy of the molecule in the initial state E is equals to sum of electronic energy, vibrational energy and rotational energy in their initial state, and energy of the molecule in final state will be E is equals to E dash E plus E dash V plus E dash R, that is electronic energy, vibrational energy and rotational energy sum in their final states. Energy change involved in the electronic transition will be given by energy of the molecule in final state minus energy of the molecule in initial states. Delta E will be equal to E dash minus E. But according to Planck's quantum theory, delta E is equals to h nu, that is hc nu bar, where nu bar is equals to del E of electronic energy, del of vibrational energy plus del of rotational energy upon Hc. As for a particular electronic transition, so that del electronic energy remains constant, and for a particular vibrational transition, so that vibrational energy remains constant, and change in rotational energy can have different values due to different rotational transitions within the same vibrational energy change of the same electronic energy level. A number of closely spaced lines are obtained. This constitutes a band. For each vibrational transition, separate band will be obtained. Thus, due to different vibrational transitions for a particular electronic transition, a set of bands is obtained, called the band group or band system. Each electronic transition will give a band system and hence the complete electronic spectra involving different electronic transition give rise to a series of band groups. Thus, the electronic band spectrum obtained for a gaseous molecule is quite complex. In spite of complex nature of the electronic band spectra, these are preferred over the other types because these are obtained in the visible and ultraviolet regions so that these can be easily photographed and studied. Calculation of dissociation energy of molecules. A study of the electronic band spectrum reveals that at one end of spectrum, the distance of separation between the lines becomes small and smaller till ultimately the line spectrum vanishes and space of continuous emission starts. The frequency corresponding to the point where the line spectrum vanishes is the frequency necessary for dissociation of the molecule into atoms. Thus, electronic band spectrum can be used not only for getting the information as given by the vibrational rotational spectra, but it can also be used in evaluating the dissociation energy of the molecule. Then we will discuss about potential energy curves and Frank-Condon principle. The explanation of electronic band spectra and dissociation energy can be early understood in terms of potential energy curves and Frank-Condon principle as follows. The potential energy curve of a diatomic molecule is obtained by plotting the potential energy of the system versus internuclear distance between the two approaching atoms. The curve obtained is of the shape shown in figure 3.38. However, even at minimum energy position, that is equilibrium position, represented the point x, the atoms are vibrating so that the internuclear distances keeps on changing. Therefore, the potential energy keeps on oscillating about the minimum position. The vibration levels thus occupied by the system may be represented by horizontal lines and indicated by appropriate vibrational quantum numbers. If sufficient energy is supplied so that system occupies the vibration level represented by Vd, the corresponding internuclear distance should become infinity. That is, the molecule should dissociate into atoms. However, this usually does not happen because before this stage is reached, the electron jumps to the higher energy level. That is, electronic transition takes place and the dissociation will take place only of the molecule in the higher energy level. Now, every electronic state has its potential energy curve. Two such curves for the lower electronic states are shown in figure 3.39. They differ in the fact that the minimum of the potential curve for the excited state 2 is at a larger internuclear distance than the ground electronic state 1. The dissociation energies for the two states are different as shown in figure 3.39. This is evidently due to the fact that the bonding in the excited state is weaker than in the ground state. The vertical distance between the minima of the two curves gives the difference between the electronic energy of the two states. The transition between the two electronic states takes place according to the Frank-Condon principle explained below. According to this principle, nuclei being much more massive than electrons, an electronic transition takes place much more faster than the nuclei can oscillate to change their internuclear distance. An electronic transition takes place from an extreme end of the vibration level, example from A or A dash as shown in figure 3.39, because the velocity or vibrational energy of the atoms is zero at these positions and they spend maximum time at these points. As internuclear separation remains the same, the transition can be represented by a vertical line, for example from point A dash to a point C of the upper point, and note from potential energy minimum of lower curve to that of upper curve. The new vibrational level must be 1, which is nearest to point C. Counting levels, it appears that the excited molecule will be in the third or fourth vibrational levels of the state 2. This explains why in the electronic transitions there is no simple selection rule for the transitions among the vibration levels. All types of transitions from lower vibrational level to any of the vibrational levels of higher electronic state are possible. It may be mentioned here that according to quantum mechanics, the transition from the all types of transitions from lowest vibrational level to any of the vibrational level of higher electronic states are possible. It may be mentioned here that according to quantum mechanics, the transition from the lowest level takes place from the midpoint of the vibration level, which is the equilibrium or the most probable position, and not from the extreme positions. Each vibrational level has a large number of very closely spaced rotational levels which have not been shown in the diagram. Now, when the transition takes place from the vibrational level of the lower electronic states to some vibrational energy level of the upper electronic state, it is accompanied by a number of transitions between the rotational levels. The result is a group of closely spaced lines called a band. Since a number of vibrational transitions takes place, a group of bands, that is the band system called band system, is obtained. Further, as the transitions takes place between many different electronic states, the result is electronic band spectrum consisting of several band systems. If electronic transition similar to A-C takes place, the result is an adsorption spectrum consisting of a number of vibrational bands. If, however, a transition similar to BD takes place, where point D represents the vibrational level corresponding to which the internuclear distance is infinity, the molecule dissociates. Thus, when such a transition takes place, the absorption spectrum consists of a number of bands corresponding to transitions from the ground state to definite vibrational levels in the upper state, but these bands will converge and finally pass into a continuous region or continuum which has no fine structure. The point at which the continuum starts is called the convergence limit. The frequency and the hence, the energy corresponding to this limit gives the dissociation energy of the molecule. However, it is important to note that after dissociation, atoms are produced in the electronically excited state and not in the ground state. Hence, to obtain the energy of dissociation into ground state atoms, the excitation energy of the atoms must be subtracted. Lastly, it may be pointed out that if the minimum of the upper electronic state is nearly at the same internuclear distances as that of the ground electronic state, the transition from V0, if the ground state to V is equals to 0 of the upper state, that is 0 transition, is the selection rules for electronic transitions in molecules. In order to understand selection rules for electronic transition in molecules, we should first understand a few terms and symbols to be used therein. First term is parity. Parity represents the behavior of the orbital with respect to inversion. It is used for the molecular orbital of homonuclear diatomic molecules. We consider a point in the molecular orbital and note the sign of the orbital wave function. Then we travel equal distance through the center of the molecule to the point, that is center of inversion, on the other side. This operation is called inversion. If at this point the orbital has the same sign, it is said to have an even parity and is denoted by G from Grad, that is German word for even. If the orbital has opposite sign, then it is said to be have odd parity and is denoted by U for ungerad, that is uneven. The parity designations apply only to homonuclear diatomic molecules because heteronuclear diatomic molecules like HCl do not have center of inversion. As shown in figure 3.41 below, A bonding sigma orbital has even parity and is written as sigma g. A sigma star orbital has odd parity and is written as sigma u. A bonding pi orbital has odd parity and is denoted as pi u. And a pi star orbital has even parity and is denoted by pi g. Molecular orbital involved in electronic transitions. The most common molecular orbital present in a molecule are the bonding molecular orbitals sigma and pi and the corresponding antibonding molecular orbitals sigma star and pi star. Besides these, there may be heteroatoms such as N or O present in the molecule which have orbitals containing lone pairs of electrons. As they are non-bonding orbitals, they are designated as n orbitals. They do not have any corresponding anti-bonding orbitals. In case of homonuclear diatomic molecules such as H2, N2, etc., the highest occupied molecular orbital HOMO in the ground state is a bonding molecular orbital BMO, whereas the lowest unoccupied molecular orbital LUMO is an antibonding molecular orbital ABMO. The electronic transition takes place from HOMO to LUMO on adsorption of suitable energy. The transition may also take place from n orbital to the antibonding molecular orbital. In other words, the electrons may be excited from uh, sigma, pi or n orbital to sigma star, pi star orbitals. Thus, the transitions which are allowed are sigma to sigma star, pi to pi star and n to pi star or n to sigma star. The type of transition involved depends upon the nature of compound and takes place by absorption of frequencies characteristic of the compound or the group present. Taking the example of carbonyl compounds, that is aldehyde and ketones, the sigma, pi and n orbitals and their excited state are shown in figure 3.42. Thus the transitions taking place are n to pi star at lambda is equals to 280 nanometer and pi to pi star at lambda is equals to 180 nanometer. Further, it is interesting to point out that if a single electron excited from the lower orbital to the excited antibonding molecular orbital has a spin opposite to that of electron left in the lower orbital, the total spin of the excited state is S is equal to 0. So that multiplicity is equal to 2S plus 1 is equal to 1. Hence the excited molecule will be in singlet state. If the two electrons in the upper and lower orbital have parallel signs, S is equal to half plus half, that is equal to 1. So that 2S plus 1 is equal to 3. That is, the excited state is triplet. Thus, excited states are classified as singlets or triplets. The triplet state has lower energy than the singlet state in accordance with Hons rule. Uh, as already explained, oxygen in the ground state is in the triplet state. It shows an exceptional behavior as the electronic transition takes place from triplet ground state to triplet excited state instead of singlet excited state. That's why the spectrum of O2 molecule is quite complex. The types of transitions which certain categories of compounds undergoes, the reason or the wavelength absorbed for these transitions are given below. Saturated hydrocarbons or compounds containing carbon-carbon and carbon-hydrogen single covalent bonds require very large energies to produce electronic excitation, usually beyond 160 nanometer. In such molecules, such sigma to sigma star transitions takes place. A simple olefin has an absorption band at about 170 nanometer. In such molecules, pi to pi star transition takes place. Molecules like methylamine and methyl iodide, which do not contain pi orbital, undergo N2 sigma star transitions. All electronic transitions in organic compounds do not occur in the ultraviolet region. The occurrence of colored compound indicates absorption of radiation in the visible region. Compounds containing N double bond N group or long conjugated system of double and single bonds, including aromatic rings, absorb at wavelength greater than 180 nanometer. That is why they look colored. Such groups are called chromophores. In such cases, the energy of the molecular orbital to lie close together, pi to pi star transitions take place. For example, the protein beta carotene has a fairly long conjugated spectra and shows absorption at about 240 to 280 nanometer intensity of electronic bands. The intensity of any electronic band depends upon the extent of overlap between the wave functions of the ground state and the excited state. Greater the overlap, greater is the intensity. As there is a very poor overlap of the wave function in the N2 pi star transitions and there is excellent overlap in the pi to pi star transitions, the intensity of the band produced by N to pi star transition is very low as compared to that produced by pi to pi star transition. Further, in the presence of an acid, the electrons of the n orbital undergo protonation and the N to pi star band disappears. And here our topic electronic spectra ends. Thank you.